Hey class, and welcome back. We're now going to talk about the second chunk of material from chapter 14, talking about my very favorite force, buoyancy force. So here's part B, buoyancy force. So my question to you all is, why do objects float in water? Have you ever thought about this, how amazing and incredible it is? Like, take for instance, I've been on a cruise before, right? So there's this massive ship, right, with hundreds or even sometimes thousands of paying customers on there. And then on top of that, thousands of people to take care of those people, to make their bed and prepare their food and so on, right? You have just thousands of people, all the food for those people, all their beds, all their furniture, all their drinks, all this crazy stuff shoved into this giant metal container, a boat, right? And all of that is able to float, not only to float, but to move around and to float to where a large portion of the object is actually above water. You have all of that mass and that big thing, and it's still able to float. How is that possible? What makes it possible from a physics standpoint? So to think about this, let's get back to exactly where we started, right? If you remember before, okay, you have an object submerged in water. And so there must be some force pushing up on an object in water that's going to make it want to float, or at least resist it from sinking. If you were to take a rock, even a rock, something that sinks, and drop it in the water, it might fall fast in the air, but once it gets to the water, it's going to fall much slower. Part of the reason it falls slower is because of drag in the water, but part of it is also a result of this force, known as the buoyancy force, the force that makes things want to float. So how do we quantify then the buoyancy force? Well, the buoyancy force acting on an object is going to be a result of the difference between the forces on the bottom and the top. Because what is it that gives rise to buoyancy force? What makes things float? It's actually just the difference in pressure at different depths. So why does an object submerged in water, why would this thing float? Because there's more pressure on the bottom and less on top. This is crazy to think about. Imagine if I had a balloon here, right? If I had a balloon, why could it float if it had helium in it? Well, it could float. A lot of people would say, well, the helium's less dense than air, all these reasons. Yes, that's all true. But the reason that it's able to float is because there's a buoyancy force acting on it. Why is there a buoyancy force acting on it? Because the pressure right here in this room, it's just a little bit higher than the pressure right here. And that's just a little bit higher than the pressure right here. So if I have a balloon, there's more pressure under it and less on top. Pressure is force over area, so there's a difference in the pressure, and that difference in the pressure pushes it up. So the pressure gradient that we talked about in the last video is so important, partly because it gives rise to the buoyancy force. So if I had this object and I wanted to quantify what is the buoyancy force equal to, well, I know it'd be a difference in the pressure on bottom versus the pressure on top, but I want the force. So force is pressure multiplied by area. So the difference between these two would be force at the bottom minus force at the top, or the change in pressure multiplied by area. But what is this change in pressure going to be equal to? How do we know how different the pressure is down here versus up here? Well, we learned that before, right? The difference in pressure is just rho GH. So the buoyancy force then, acting on this object, is just going to be equal to rho GH times the area. Now, what are these different things? Here, this is the area of the bottom or top of my cylinder, but how does that work for my balloon where it's curved? Or how does that work, for a boat or something like that? Well, it gets tricky, so we're going to have to do some more substitution. And this density here, don't forget, that's the fluid, not the object. So that's the density of the water in this case. Okay, so we know, though, that the total volume of this object is just its height multiplied by that surface area, because it's a cylinder, right? So what we can say then is the buoyancy force acting on this object is just going to be equal to the density times the volume. So this is the density of the water. This is the volume of the object. But guess what? The volume of the object is just the same as the volume of the water being displaced times gravity. So what this is saying, and this gives rise to what's known as Archimedes Principle, buoyancy force is just equal to the weight of the fluid being displaced, the mass times gravity of the fluid being displaced. So how much buoyancy force is acting on a rock when it's in the water? It's just the volume of the rock times the density of the water times gravity, or the weight of the water being pushed out of the way by that rock. What about that giant cruise ship we were talking about? How much buoyancy force is acting on it? Well, it's just the weight of the water that it's displacing. What does that mean for displacing water? Well, it's the weight of the water being pushed out of the way by the boat. So Archimedes' principle tells us that the buoyancy force, the upward force of an object immersed in any fluid, is equal to the weight of the fluid being displaced by that object. All right, so again, the magnitude of the buoyancy force is equal to the weight of the fluid displaced. So right now, I'm sitting in a room. I'm in a fluid. I'm in air, right? There's an upward buoyancy force acting on me, and it's equal to the weight of all of the air that I'm displacing. So if you take a Todd-sized cutout of air, figure out what its weight is, that's how much buoyancy force the air is pushing on me. It's not that much because air is so light, I hardly notice the difference. I'm much heavier than it. I know, thanks for calling me fat. No, but now if I go and jump in my pond in the backyard, I will be displacing a Todd-sized chunk of water, and that Todd-sized chunk of water weighs a lot. In fact, it almost weighs the exact same as I do. And so I feel a much greater buoyancy force to where I can approximately float in that water. Pretty interesting, right? So again, buoyancy force is equal to the weight of the fluid being displaced. Weight of the fluid being displaced. So if you think about this, what if you have an object that's floating? A big cruise ship, for example, right? If you have an object that's floating, what's the buoyancy force going to be equal to? Well, if it's floating, what's its net force? 0. It's got weight going down, buoyancy force going up, then the buoyancy force is just equal to the weight of the object. So how much water is it displacing? If it's able to float, it's displacing water equal in weight to that object's own weight. So those big cruise ships again, guess what? They're displacing the amount of water equal to the weight of the cruise ship, the people on it, all the food, everything. All of that has a lot of weight, but it's able to displace an equal amount of water, and so therefore it floats. Does that make sense? I hope it does. So how do hot air balloons work? Hot air balloons also use buoyancy force, but they're a little bit tricky, okay? What's the deal with the hot air balloon? Take a minute, pause the video, think about how do they work? Think about their mechanisms and so on. Here's a picture to help motivate you, okay? How do hot air balloons work? Well, again, it's based on buoyancy force, so the fact that there's more pressure underneath than there is on top. But here's what's pretty cool, what they do, okay? So you start to fill up a hot air balloon. Let's imagine it's still on the ground. It starts to fill up, it gets all taut and everything, but it's still not floating, right? It's displacing as much air as it can to generate as much buoyancy force as it can. But guess what? Net force, maybe I'll write this over here just so you don't get confused, okay? Right? Net force, some of the force is in the y direction. If it's on the ground, it's going to be 0, and the net force is the weight of your object. Let me write this down. Let's do a free body diagram here in case you can't see. Maybe I should pop this up a little bigger. Okay, so free body diagram, we got the weight of the object going down, and we have the buoyancy force going up, right? So some of the forces, you got buoyancy force minus the weight of the object equals 0. So if your hot air balloon is not floating up, that means that its weight is bigger than the buoyancy force. Okay, so if it's on the ground, it has the normal force also pushing up. You want to get it to where the normal force is 0, to where the buoyancy force is equal to the weight, and then maybe even to where the buoyancy force is slightly more than the weight of your object. But when you're talking about a hot air balloon, what weight are we talking about here? Well, what we're talking about is the weight of the balloon itself, right? All of this has mass here. This outside thing has mass as well. But then you also have all of this air inside also has mass of the air inside here. And so this mass is all of this added together. Okay, so what do? You start a little fire right here. You heat up the gas inside, and as it heats up, air starts to move out the bottom, and this becomes less and less massive as you decrease the density of the air inside by heating it up. And so you get more and more air moving out. This mass goes down, and eventually you're able to start to float. Fun fact about hot air balloons, why or when do you see them, I guess I should say? Well, you always see hot air balloons, you usually see hot air balloons first thing in the morning. Why is it that they launch first thing in the morning? Any guesses? Well, Because you can get more buoyancy force in the morning. What? Why? Sounds weird. Why can you get more buoyancy force in the morning? Well, you can get more buoyancy force in the morning because it's colder, and therefore the air is more dense, and therefore the air you're displacing weighs more. So there's more buoyancy force because the air you're displacing weighs more. Fun fact. I love buoyancy force. It's so good. Cool. Actually, I have a fun video about buoyancy force. I'll post separately for you guys to check out. It's one I made with my wife, actually on her birthday. So here's an example problem for you all about buoyancy force. Here's a raft. I don't know if you've ever seen these. Let's say it's a big chunk of pine wood, a bunch of boards nailed together that you can go and jump off of to do fun tricks in the middle of a lake or something. All right. So here's the object. We're told it's 4 by 4 square meters. All right, so I want you to tell me whether or not this object is able to float. Okay, I forgot to tell you the thickness. All right, so it's 0.3 meters thick. You need that as well. So I want you to tell me, first of all, if it's able to float. I'll give you a hint. Probably it is, but prove it to me. Okay, but the second question is, how far in the water is it going to sit? How deep in the water is it going to be riding while it's floating? Figure that one out for me, and then we'll check and see if you got it right. But first, prove to me that it floats, and then tell me what h is. Okay, ready, go. So let's go ahead and tackle this one. Hopefully you already paused and figured it out. So first of all, let's find the volume of the raft. The volume of the raft is length times width times height. So it's 4.8 cubic meters of raft. And so the maximum possible buoyancy force that the raft could generate is if the entire thing were in the water. So it'd be displacing 4.8 cubic meters worth of water. So the maximum possible buoyancy force is going to be the density of water multiplied by that volume multiplied by gravity. Do the math, and so the max buoyancy force is about 47,000 newtons. If we go back, the raft itself has a mass of 2,640 kilograms, right? So if we compare this, that is equal to approximately 26,000 newtons. So the mass of the raft, yeah, it's quite a bit less than the the weight of the raft is quite a bit less than that maximum possible buoyancy force. So that means it floats, right? The maximum buoyancy force is more than the weight of the raft. So then, in that case, what is h? Well, if it's floating, then we know buoyancy force equals the weight of the raft. Cool. So buoyancy force equals the weight of the raft. Buoyancy force is density times volume times gravity. Density times volume is the weight of the fluid displaced, right? Okay, and the weight of the raft we know is 26,000 newtons. Now, what is the volume of water being displaced? Well, it's going to be length times width times height, this h. So 4 times 4 times h. We got g is 9.8. We got the density of water. So now we just solve for h, do the math. But bada bing, bada boom, box worthy. We get 0.17 meters. So what we find is that slightly over half of the raft is actually in the water. And this makes sense, right? If we go back to when we proved that it could float, the weight of the raft was slightly over half of the weight or the maximum possible buoyancy force. Okay, so you should have got 17 centimeters or 0.17 meters. All right, so the last thing I got for you on buoyancy force and Archimedes Principle is another conceptual question. It's kind of a fun one to think about. Again, I love ships, especially old, 3-masted big sailing vessels, really fascinating to me. So imagine you have a ship, all right, and you can have it floating in the ocean, obviously. But my question to you all is, so if you're in the ocean, there's obviously tons of water for it to displace, and so it's going to float because it has all this water to displace. Could you take a big boat or big cruise ship like the ones we're talking about earlier, and could you float it in just like a swimming pool's worth of water? What do you think? Yes or no? What if the swimming pool is smaller than the boat itself? Okay, let me rephrase that. What if the amount of water is less than the volume of the boat by a lot? Could it float still? Well, it's a weird question, right? You're like, I don't know, like it would just hit the sides. No, I mean, if you had the right size and shaped object, could you still float it with just a little bit of water? And the answer is yes. And you'll actually see this in different lock mechanisms, things like the Panama Canal and so on. You can actually have a large, very massive boat being floated on just a very thin layer of water on all sides. Because even though that water is not there to actually be displaced, it's still going to experience the buoyancy force due to the pressure at all points along here, right? The pressure down here is higher than the pressure up here because it's part of the same chunk of water. And so therefore you could still float even with just a, a millimeter thick layer of water at all points. You can have an object floating, not dissimilar from hydroplaning and things like that. Well, kind of dissimilar. But anyway, a very, very thin layer of water could still make your object float. All right, so I've gone on about buoyancy force for quite some time. So again, to prevent my videos from getting too long, I think I'm going to cut it here, and there'll be one more section, part C of chapter 14, where we talk about fluids in motion. Have a box-worthy day.